and welcome back. So today we are heading into linearization and differentials, which sounds, when you just say those words, it sounds like it might be something complicated, but it really is not. So I want to try and make this sound as simple as I can. Say you have a function, f of x. If I ask you to perform a linearization, all that really means is this. All that really means is at a given point, here you have a given point. Let's say you run a tangent line, through that given point. What we're really getting at is, as long as you stay within some epsilon neighborhood, isn't the tangent line a good approximator for the function? Meaning, won't it produce functional values that are arbitrarily close to the functional values that truly exist on the function, as long as you stay within some epsilon error tolerance, okay? So for example, here I'm going to look at this first picture. Y equals x squared and its tangent, y equals 2x minus 1 at the point 1, 1. So, the tangent line acts as a good approximator for functional values as long as we don't walk too far away from what's called the center of the approximation. And we're using the graphing calculator. Here's the tangent and the curve very close near the point 1, 1. So we use that like zoom in feature of the calculator. Okay? Tangent and curve very close throughout the entire x interval shown. So basically you keep hitting zoom in, and if you keep hitting zoom in, you're on such a tiny interval, and you can see sort of the values here. You're on such a small scope that you can barely distinguish. It says the computer screen cannot distinguish the tangent line from the curve on that particular interval. So the big gist is, okay, as long as we can tolerate some error, we can use, the whole point of linearization is that you can use a simpler function to produce to give you an estimate of what the functional values are, okay? You can use an easier function. So you say, as long as you can tolerate error, how much error? So that's a deeper discussion later. We'll look a little bit at, how much error would exist if you were to do something like that. Okay. So a little bit more notation and language here. So here we have a function, y equals f of x, and the slope, y equals f prime of a, so the slope at a point, and then y equals L of x. So notice, y equals L of x, which we used to call y equals mx plus b, the tangent line. So the tangent line is the linearization at a certain point. So when I ask you to perform the linearization at a certain point, I'm really asking you to get the equation of the tangent line. So let's take another look. So here we're just reiterating that the tangent to the curve at a certain point is the line, and notice how we used to call the tangent line y equals mx plus b. Well, y equals mx plus b, that's, you remember from algebra, that's slope-intercept form. So instead of calling it that, if you think about point-slope form, y minus y1 equals mx minus x1, if you think more about point-slope form, that's what we're giving here. So when we determine L of x, the linearization at a certain point, you can see that if we use point-slope form, we could arrive here. So it's the function evaluated at a plus f prime evaluated at a times x minus a. So a lot of people see this and they think it's some new fancy formula. It's not. It's really just stemming from, point-slope. So if you take point-slope form, I'm just going to highlight here, point-slope form. And, y1 is really the function evaluated at a. So if you swing y1 back across the equal sign, right, you'd have y equals, y1 plus m x minus x1. And if you think about it, what's y1? Function evaluated at a. And what's the slope? The derivative evaluated at a. And, x minus x1, well, x1 is the point that's given. Okay? So all we're really doing is saying that L of x is still the equation of the tangent line. It's just that we're sort of stemming that off of point-slope form rather than y equals mx plus b form. So, okay, so you will, for the purposes of this section, you will want to wheel and deal with L of x in that form. So function evaluated a plus f prime evaluated a times x minus a. makes the computation easier to do, as we will see right about, yes, here. So the next thing that I want to do with you is it says let's perform two linearizations to the function y equals the square root. I wrote it like that, but I mean square root of 1 plus x. I want to perform a linearization at x equals 0 and then, at x equals 3 respectively. How accurate is this approximate for values of x near the center of the approximation? So here's the results for L of x at x equals 0. But let's first, those are the results, but let's first actually crank this lovely thing by hand. So you want to start, when you perform a linearization, you just want to start by reciting the formula. So, you have your original function, and L of x is equal to f of a plus f prime of a times x minus a. Okay, so your function evaluated at a, and here a was, we want to choose values of a near, well, at first, at a equals 0, and then later we'll do it at a equals 3. Okay, so function evaluated at a, so let's go ahead and take 0 and put it right there. And you can just do that mentally. 0 plus 1 is 1, square root of 1 is 1. So we know f of a is 1, plus, now this might take some thought, the derivative evaluated at 0. So what I would do is just kind of go off on the side and say, well, what is the derivative? Well, it'd be the square root of x plus 1 really means x plus 1 whole thing to the 1/2 power. So its derivative would be, 1/2 x plus 1 whole thing to the negative 1/2. Okay, just kind of noting that off on the side. So if I take 0 now and store it into the derivative, well, 0 plus 1 is 1. 1 to any power is still 1. And then times 1/2. So now I know that's going to be 1/2. So the derivative evaluated at 0 comes to be 1/2. And then square root of x plus 1. So let's go ahead and store 0 in here. So 0 plus 1 is 1. Sorry, I just noticed I had something written wrong on my notes there. That was just me copying down wrong. So again, L of a is, f of a plus f prime of a times x minus a. So here, you're just plugging your a into here. So your a is 0. Okay. So we have at this moment, L of a is equal to 1 plus basically 1/2 x. So 1 plus 1/2 x would be our linearization. So what that means is for values near the center of the approximation, so for values very near 0, we should get something, a functional value that's close to what the true functional value is. So let me highlight this in another color back here. I'm going to highlight what this table is kind of showing you now. Let me do this, pick blue here. Okay, so this means let's take values near the center. So say 0.005. So you pick something near 0, 0.005. Well, if you store that, see, into here, into L of a, you're going to get 0.005 divided by 2 plus 1, which is 1.00250. But now, if you store 0 into the original function, not 0, I'm sorry. If you store numbers near 0 into the original function, say 0.005, store that into the original function, which was y equals root x plus 1. Well, if I put, and I'll do it on my calculator with you, 0.005 plus 1 is something, right? 1.005, and then square root it, guess what you're going to get? 1.00249. You're going to get this number here. So what I want you to note here is estimate true, and then this is the difference. Okay? So if I walk out a little bit away from the center of my approximation, say 0.005, and I'm still gonna get a functional value that is very, very close to the true functional value. So the estimate and the true value are within very close distance of one another. And then you say, okay, well, what if I walk out a little bit further? You know, and that's where I'm really just going to highlight here, 0.05. So now I'm walking out further away from 0, 0.05. Well, then what happens is my estimate, you know, using this L of A, will be 1.025, but the true value will be 1.02469. So there's becoming a larger difference there between the values. Okay, and that's what really this is saying here, the difference between the estimate and the true. So what that means is as we walk further away from the center of the approximation, the model becomes bad, you could say. So you say, all right, well, it would clearly be, this L of A here would clearly be crude for, say, x equals 3, because I'm walking far away from this, you know, from 0. So you say maybe you have to perform a new linearization because you've walked so far away. So let's try that. Let's take that very same function. This will be just good practice. You see I'm erasing here. Let's take that very same function and perform a linearization at x equals 3. Okay, so my pen's acting fussy, forgive that. So we have, we have y equals the square root of x plus 1, but now I want to find L of A, and this time at x equals 3. Well, then that's going to be f of A plus f prime of A times x minus A. Alright, well now just go ahead and take 3, store it into the original function. This means function evaluated at A. So 3 plus 1 is 4, square root of 4 is 2. So 2 plus, now the derivative evaluated at 3. Now remember I had erased it, but the derivative was 1/2, you know, x plus 1 to the negative 1/2. So we're sort of rerunning that procedure. If you store 3 into the derivative, well, 3 plus 1 is 4, and 4 to the negative 1/2 power is like 1 over 4 to the half power, which is 1 over 2. So 1/2 times 1/2 is 1/4. So basically the slope ends up being 1/4. The derivative evaluated A is 1/4. And then times x minus A. Okay. So now if I crunch this out, I'm going to have 1/4 x minus, so I'm going to have 2 plus 1/4 x minus 3/4. But you want to keep cleaning that up, you know. So 2 minus 3/4 is 1.25, which is 5/4. So your linearization then would end up being 5/4 plus 1/4 x. So you see there, and then you could run that same experiment if I go out a little bit away from 3, you know, say 3.005. And see, and notice the linearization is keyword linear. So it's linear, so you're ending up with a lot simpler function than the original, and still going to produce functional values that are arbitrarily close to the true functional values. Okay, I'm going to hit pause a second. Now I think we're ready to go a little bit deeper, so there's going to be some language and notation here. Let y equals f of x be a differentiable function. Then the differential dx is the independent variable, and the differential dy will be denoted this. Okay, so notice that dy is really f prime of x dx, but the thing is you already know that, because you know that dy dx is notation for f prime of x. So even if you just use some basic algebra and multiply, you know, both sides of the equation by dx, that you would know that. Okay, so in other words, dy is the change in linearization when x equals a changes by amount delta x. So what I can tell you, a little bit of more notation, next we're going to look at delta y versus dy. So dy, I can tell you, is remember when we said in this segment we're always looking on the estimate for the functional values versus the true functional values? So true change in functional values, and this is the estimate change in functional values. So say we're interested in change in y equals f of x, so change in functional values near a point x equals a. Well, if is a differentiable function at x equals a and x changes from a to say a plus delta x, the delta y in f is given by delta y equals, and here I'm going to translate this, f prime of a delta x. That's really saying your estimate, because we see now, we use the derivative, that's really your estimate plus some error tolerance. And if you think about it, if you translate that, it makes sense. It's saying that the true change is always equal to the estimated change plus some error. So true change in y equals the estimated change plus some error. Well, the easiest way we can show this is to do a book example. I know the notation looks a little scary, but when you see this, it should make it fairly clear. Okay. Here we have a function that's given to us, and it says for each function f of x changes value when x, so I cherry-picked a problem from the book basically. Our function is going to change values when x changes from x to x naught plus dx. In phase 1, we want to find the change delta f. Remember, that means true change. And, and then in phase 2, we want to find the value of the estimated change. So true change, delta f, estimated change, df. And then the approximate error, that means we're always interested in the difference between the true change in functional values versus the estimated change in functional values. Okay, so we have to be given a function though, so let's see what function we were given. Okay, so I have it right here. F of x is equal to x squared plus 2x is our function. X naught is 1, dx is 0.1. So the true change I like to think of it as true change. It's really just, f of b minus f of a. So the function evaluated b is like when you walk out. So here's x naught, 1. dx is 0.1, that's change in x. So if I walk out 0.1 further than 1, I'm at 1.1, right? So store 1.1 into the original function in place of x. I'll do it with you. So 1.1 squared is something plus 2 times 1.1. So I'm just typing that out in the calculator. 3.41. 3.41. And then, minus function evaluated at a. So minus the function evaluated at 1. Well, function evaluated at 1, f of 1 is equal to 1 squared plus 2 times 1. So that's 3. So 3.41 minus 3, that's 0.41. So the true change, the answer to part A, the true change in values is 0.41. Now it says get the value of the estimated change df by simply taking the derivative evaluated x naught times dx. Okay, well let's do that. Here's your function. So its derivative, I'm going to call that f prime of x, is equal to 2x plus 2. Now, to use a little bit more notation, I'm going to, instead of f prime now, I'm going to call that df dx. So the derivative of the function with respect to x is equal to 2x plus 2. If I just kind of swing that dx up here, really means like multiply by dx. Okay, then I'm using what they told me to use to calculate the estimated change. So I'm going to take 1 basically I'm going to take 1, I'll do this in another color, take the givens, 1, store it right there, and take the dx, 0.1, and store it right there. Okay, let's try it. So 2 times 1 plus 2 is something, and then times 0.1. What do we get? 2 times 1 is 2, plus 2 is 4, and 4 times 0.1 is 0.4. You could say 0.40 or 0.4. Aha! So the estimated change, and notice this, the true change was 0.41. The estimated change was a 0.4, and then we take that difference, you know, in absolute value here. So the approximate error is only 0.01. So note to self, the error is only 0.01. It's very small. You say, how small is small enough? Well, we'll get to that later in chapter 10. But at least now you know the language. The main thing is the language exposure. So delta F with the triangle is a true change in functional values, and df is estimated change in functional values. Now the df is the one that requires the derivative. Okay, the df is what we found right here and plugged in the given information, and we found that the df ended up being 0.4, which wasn't far away from the true difference in functional values. And that's what we mean by differentials. Okay? All right, good luck with this section, guys.